Hello, today we are in Course 2, Session 4 of Technology Fundamentals, covering the topics of model selection and validation. At the end of Session 1 this week, we saw the basic recipe for creating a supervised machine learning model. We set up our environment, we imported data. We then did a rudimentary exploratory data analysis, or EDA. We then did a little bit of feature engineering, albeit on Monday it was very simple, involved removing null values, deciding which columns to use in our model. We then chose and trained a model. This consisted of choosing the model type, setting hyperparameters, fitting using training data, and predicting using validation data. I put training and validation in parentheses because we actually didn't split up into train and test sets in our main time together. We had this as an enrichment exercise. Today we will be giving exclusive attention to divvying up our data between training and validation sets, and we'll talk about why as well. In that session, I chose our model and hyperparameters preemptively. How did I do that? In the real world, we won't necessarily have the best intuition about how to make these choices. And so in today's session, we will algorithmize the way we approach choosing and training a model. I will use and import libraries at the beginning of this notebook, as is good practice, but I will do my best to re-import them as they're used in the notebook to remind ourselves where they came from. Importing our packages, some of these we've seen several times before. We should have some familiarity with SciPy and stats models now. We saw it yesterday. Our main workhorse today will be the sklearn library. To start with, we will load a very famous data set called the IRIS data set. And we're going to use this in the beginning here just to motivate the usage of train and test sets. We don't care too much about what these data are other than our X data, that is our independent variables, are going to have 4 different features, and our target is going to be a single value that classifies the input data based on those features. We're also going to import our wine data set. All right. Model validation. The way we're going to motivate the use of train and test sets is we're going to do a supervised learning model without train and test sets. So we're going to do this the wrong way first, and we're going to use that to motivate doing it the right way. The supervised learning model we're going to use is k-nearest neighbors. K-nearest neighbors, or KNN, is perhaps the simplest algorithm of them all. It is essentially a lookup table. We select the hyperparameter k, which is the number of neighbors we care about. And when assigning a new value a data label, assign it according to the majority label in the vicinity of the new data point. That vicinity is determined by k, the number of neighbors we care about. So I'm going to create my model object KNN, calling upon the k-nearest neighbors regressor method in sklearn. I'm going to set k, or the number of neighbors I care about, to 1. And I'm going to fit to all of my data x and y. I'm then going to score the performance of my model on that same data. And I get a score of 100%. Crazy, right? But is this how we really expect our model to perform out there in the real world on unseen data? Probably not. So how do we actually check the performance of our model? To do this, we introduce holdout sets. The way we account for unseen data in practice is to leave a portion of the data set out for testing. This way we can estimate how our model will perform on entirely new data it may come across when it is put into production. The way we do this is traditionally with sklearn's train test split method. I feed it the X data, the Y data, the portion of the data I'd like to reserve for either testing or training. We'll see we have 2 different parameter flags to choose from here. We can seed that train test split module with a random number, so it operates the same way every time. And then we proceed as before, except this time we fit with our training data and test with our testing data. I mentioned this, we can also choose a train size instead if we are interested in doing that. And then if we want the behavior to be the same, we just use the reciprocal, 0.6 versus 0.4. And in either case, we see that we get a more reasonable value for our performance, 97% accuracy rather than 100. All right, data leakage and cross-validation. An even more rigorous method to leaving out a single test set is to perform cross-validation. Imagine a situation where we are trying to estimate the best value of k in our KNN algorithm. Remember, k is a number of nearest neighbors we care about when assigning a label to a new value. If we continually train our model with new values of k on our training set and test with our testing set, quote, knowledge of our test set values will leak into our model as we choose the best value for k based on how it performs on our test set. Keep in mind, this is even though we did not train on this test set. We call this phenomenon data leakage. CV, or cross-validation, overcomes this by only evaluating our parameters with our training set. This schematic here I like. It can be a little confusing at first because of the way we've divided up between the left side and the right side. But I will explain this so that it makes sense. With cross-validation, we take all of our training data. So right now, this box here is the same as this box here. Okay, we take our training data and we use this to search for the best hyperparameters. Okay, but each one of the models that we've used in cross-validation has not itself seen all the training data. More on that in a moment. The reason the schematic is drawn this way is once we have all the best parameters selected, we make sure to actually train our model on all of the training data. Okay, so that's why these two boxes are the same, but that's also why we've divided this up into two different sides. We then have the retrained model that is going to be our final production model, and we do a final evaluation at the very, very end with the test data. In this scheme, we don't evaluate our model on the test set until the very end. Rather, we estimate our hyperparameter performances by slicing the training set into what we call crossfolds, hence the name crossfold validation. Let me walk us through this schematic now so that we make sense of it. Here's our test data reserved for the very, very, very end. And here's our training data that we're going to perform cross-validation on. In cross-validation, according to the number of folds we've determined, in this case 5, for 5 iterations or 5 splits, 1/5 of our data set will serve as an intermediary test data set, while the other 4/5 serve as training data. So in this split 1, we fit on these 4 folds and test on this fold. In split 2, we train on this fold as well as folds 3, 4, and 5 and test on fold 2, and so on. By the end of this procedure, we had, as you might have guessed, 5 different models trained on slightly different variations of the training data, as well as 5 performances. We use those results to determine which hyperparameters are best, okay? And once we have determined that those hyperparameters are best, we retrain the model on all of the training data, and at the very, very end, test on our test data set. To make sense of this, I'm going to lead us through an example. We can import cross-val score from sklearn submodule model selection. And now we feed in our model, our training data, xtrain, ytrain, which represents this whole teal colored block up here. And we set the number of cross folds, in this case 5, just as we've designated in this schematic. Okay, and now when we run cross-val score, we get a score back that indicates the performance of our model on each one of those splits, 1, 2, 3, 4, and 5. Now that we have those split sets and we've set our hyperparameters for KNN previously up above, we can then determine that the overall accuracy of that model is 90% on the training data, based on each of those individual test sets that we evaluated on during the CV cross-validation. For more information on cross-val score method, you can visit this documentation link. And there's our handy little image. An additional topic on cross-validation is the extreme leave one out validation, and you can read more about that here in Jake Vander Plas's Data Science Handbook. All right, so we motivated the use of train and test sets. We then talked a little bit about this phenomenon of data leakage. Now we're going to move forward and talk about this other important topic, bias variance trade-off, and you will see this in all topics of machine learning and all models that we would potentially use in a machine learning scenario. In order to carry us through this topic, I'm going to make up my own data set. All right, so I've defined a function here on line 6 called func. I feed in some X data as well as an error rate. And I'm going to return y of the functional form log x, but I'm going to add a little bit of error to every output. And that's based on my input error setting. All right, so I'm making some data here. I'm plotting it along x and y. You can see the underlying functional form here, log x, but we have this sort of scattered noise around log x. We're going to use this now for our examples moving forward. So let's just fit to a portion of this data. We're going to say this data here, all those values that we've created, is our population data set. All right, so that's all the data that's out there in the real world. And now I'm going to sample from it. I'm going to sample just 10 data points. And we see the result of sampling those 10 data points here in this plot. Again, we're seeing just the x values on the x-axis and the y values on the y-axis. Now, let's take two extreme scenarios, fitting a linear line and a high-order polynomial to these data points. Keeping in mind the larger data set as well as the error we introduced in our data generating function, this will really illustrate our point. All right, so I'm going to run this block. On the left, I have a simple linear model, all right, created with sklearn and NumPy. And on the right, I have a high variance model. To be specific, an nth degree or a ninth degree polynomial. All right, so on the left, y equals mx plus b. On the right, this ninth order polynomial. And what do we notice? On the left, we limit our regression to only two parameters, a slope and a y-intercept. We say that this model has high bias because we are forcing the functional form without much consideration to the underlying data. We are saying this data is generated by a linear function, and no matter what data I train on, my final model will be a straight line that more or less appears the same. Put another way, it has low variance with respect to the underlying data, because if the underlying data changes, we don't deviate very far from this functional form of y equals mx plus b. On the right, we've allowed our model just as many polynomials it needs to perfectly fit the training data, right? Where we see that gray dashed line passing through every blue dot. We say this model has low bias because we don't introduce many constraints on the final form of the model. It is high variance because depending on the underlying training data, the final outcome of the model can change quite drastically. In reality, the best model lies somewhere between these two cases. And in the next few paragraphs, we'll explore this concept further. On the one hand, what happens when we retrain these models on different samples of the data population? And we'll use this to better understand what we mean by bias and variance. And then on the next hand, what happens when we tie this back in with the error we introduced to the data generator? And we'll use this better to understand irreducible error and how it affects our choices between a high bias model and a high variance model. All right, but starting with number one, let's go ahead and just resample our data 5 times and create 5 different models based on each sample and see how our models change. All right, so to tie this back, our original data has not changed. Our population data remains the same as we defined it in the very first cell at the beginning of this section. We are simply changing what we have sampled from the population data in order to create our models. And as we can see, depending on what data we train our model on, the high bias model changes relatively slightly, while the high variance model changes a whole awful lot. The high variance model is prone to something that we call overfitting. It fits the training data very well, but at the expense of creating a good generalizable model that does well on unseen data. Let's take our last models and plot them along the rest of the unseen data, what we'll call the population. So I'm just taking the last model that came out of this for loop, and I'm going to plot it against the wider population data. All right, so the models are those gray dashed lines. The sample used to train the model are the orange stars, and the population data are the blue stars. In particular, we see that the high variance model is doing very wacky things, demonstrating behaviors in the model where the underlying data population really gives no indication of such behavior. We say that these high variance models are particularly prone to the phenomenon of overfitting, and this is generally due to the fact that there is irreducible error in the underlying data. So this is going to bring us into that second little topic I wanted us to hit on, the effect of irreducible error on our models. Let's demonstrate the concept. So I'm going to now recreate the population data, and I'm going to set the error or the noise to 0. And so we return something that looks very, very close to our underlying functional form y equals log x. All right, so now we have no irreducible error in our data. When we go out there to acquire our data, it looks exactly like the underlying biological or physical phenomenon that is dictating its output. There's nothing affecting our sampling or otherwise. All right, a very hypothetical situation indeed. Let's now sample from this data set. The orange data are going to be our samples that we use to train our model. The blue opaque data points are the population data again. And we see that in this case, our high variance model really gets it. And this is because the data we trained on actually is a good representation of the entire population, right? Because there's no noise. But this in reality almost never ever happens. In the real world, we have irreducible error in our data samples, and we must account for this when choosing our model. In summary, we call this balance between error in our model functional form and error from succumbing to irreducible error in our training data the bias variance trade-off. All right, time for an exercise. Up until now, we've explored this idea of bias variance trade-off from a qualitative standpoint. As an exercise, continue with this idea, this time calculating the mean squared error and R square between the model and any unseen or non-training data, population data. Error metrics that we care about are R squared score as well as mean squared error. Do this for a ninth order polynomial and repeat for population data with low, medium, and high degrees of error and small and large training fractions. And we'll complete this chart below in Markdown as we do this. All right, let's see what we've got here to help us out. Change ERR to change the amount of noise in your data. All right, and it gives a suggestion here. Let's start with the low end, 0.001. This should then give me Y values based on that error. Sample the data for training. All right, X just wanted to train test split, X, Y, actual, train set. Okay, here we go. We need to change the training size. Let's start with 0.8. How about that? Solve our training data with a ninth degree polynomial. That looks good. Generate Y data with ninth degree polynomial model and X sequence. So we're using X sequence to generate a bunch of Y data. We may need to define, I think that we're pulling X sequence from above, and so we don't need to redefine it here. Let's see how this goes. All right, name mean squared error is not defined. I think we need to import this somewhere. Oh yes, so let's go to the top where we import packages, and we'll go ahead and import it there. From sklearn.metrics, import mean squared error, and we also want R squared score. Oh, there it is right there. So we can actually just take this, plop it next to R squared score, and now we should be good to go. We've done that. Let's go back to our exercise. Give this a run. Mean squared error 0. I don't really believe that. We talked about this in our regression notebook. Let's change this to an E for exponential. There we go. There's some actual error there, but very small, right? And a really good R squared. So this is for the test set. Let's see what happens when we reduce the training set size. Let's try something a lot lower, like 0.2. Pretty high R squared still. Y test, Y pred. Oh, right. Why do we think this is? It's because our error rate is so low, right? So we're just creating this situation over here. There's no real noise. Let's try to increase the error rate. What happens when we set this to 0.01? Still really low. What about 0.1? Start to get a little bit more error. That's a more reasonable R squared. And what happens when we go all the way to 1? Ooh, a really bad R squared, right? We're doing worse. We talked about why R squared might be negative sometimes. A good opportunity here to visit our memory with that idea. Remember, R squared is 1 minus the residual sum of squares over the total sum of squares, and the total sum of squares is defined as the variance in the actual data set, right? Every observation minus y bar squared and summed. So our residual sum of squares is actually doing worse than just predicting the average. That's what that means. Pretty poor model indeed. We are fitting to noise. We'll go ahead and leave it as an exercise to fill out that table and move forward. Learning curves. To move from qualitative to quantitative understanding of bias variance trade-off, we need to introduce some metric for model performance. A good one to use here is R squared, a measure of the degree to which predictions match actual values. We can import a tool from sklearn to calculate this for us. From sklearn.metrics, import R squared score. So we did that above. We're doing it again here. Considering model complexity. In a learning curve, we will typically plot the training and testing scores together to give a sense of when we have either too much bias or too much variance in our model. I'm going to go ahead and recreate the original data distribution we introduced in 113. All right, so here we go. This is the original same data that we introduced in 113. Remember, we're seeding our random number generator, so the data will actually match perfectly. Now let's iteratively introduce more complexity into our model. All right, so I'm going to create a for loop here. I'm going to call my loop through variable complexity. And I'm going to use this to set the number of coefficients in my polynomial. The more degrees we have in our polynomial, x squared, x cubed, and so on, the more we are able to fit to the training data. So we're increasing complexity. And looky here, we have our first degree polynomial in blue. That's just going to be y equals mx plus b. Second degree polynomial, we get that curve shape, and then they start to get pretty wacky. On the right, we have our scores with increasing model complexity. So r squared on y, polynomials on x, and we can see that our training test set does better and better with more polynomials, right? And this is expected because we're fitting to the training data. As we see from both plots, the score on the training data increases with added model complexity, giving us the expected perfect fit when the order is the same as the number of data points. This is part 1 of our learning curve. Part 2 consists of plotting the training data score with the testing data score. Something else I'm going to do is define the training portion of the data as a fraction of the overall population size. To keep the comparisons the same up until now, I will keep this training fraction low at 0.2. And we introduce the concept of training fractions up above with train test split in sklearn. So nothing new here. And now we've recreated the same exact thing as we did before, but we're also tracking the test set performance. And we can see that there's a peak here around the second order polynomial. As we can see, the second order polynomial achieves the greatest test set data R squared, while the highest order polynomial achieves the best training data set R squared. This learning curve is explanative of what we see generally, namely that a divergence after some degree of complexity between training and test set performances occurs. In this case, we would resolve to choose the second order polynomial as the best model for our data. And here's a little cartoonified version of the same graphic. We'd expect at some point of model complexity, our validation test set score peaks out, and it's at this point that we want to choose those parameters for our model. Considering training set size. The last piece of the puzzle we require to fully cover learning curves is the effective training data size on the model. This is why I introduced the fraction of training data parameter earlier on. Let's explore. So I've done something very similar here. I have R squared on Y. I have the performance on both the training and the testing data sets. But now on X, I have the fraction of the overall data set used for training. It's a little bit noisy, perhaps due to the fact that we don't have that much total data in our population data set, right? We have 80 data points. And so based on how we sample, there's going to be quite a bit of irregularity, right? If we've trained on some noisy parameters just by chance versus some non-noisy parameters, etc. What we see here, though, is that a trend happens generally. As our amount of training data increases, our models handle more complexity better. This is illustrated below. And so as the training set size increases, our model score tends to improve for the validation set. And at some point, the training score and validation set will agree. Another exercise. Starting with the code below, make a side-by-side plot of a third-degree polynomial and a 12th-degree polynomial. On the x-axis, slowly increase the training set size. On the y-axis, plot the scores for the training and test sets. All right, so take a look at this. We ran an SC training fraction, train and test sets. Go ahead and run it. All right, looks like we're partly there, and it's asking us to make a side-by-side plot. And we want to do this with a third and a 12th degree polynomial. So this is for 9. So let's go ahead and make this a third degree. And let's see, I don't remember. So I think it's number of rows, then number of columns. So we want side by side. So I think we do this. And now AX isn't going to be an axis object anymore. Rather, it will be an array of axis objects. So I need to set this differently, as well as lines 28, 29, and 30. All right, so that gives us part of the solution here. We will leave it as a remaining exercise to fill out the right panel. For the right panel, remember we want to access the second axis object. Here we've indexed the first one. We want to access the second one. We would also like to train another polynomial, this time with 12 degrees rather than 3, and report back the scores associated with that model. All right. As a visualization exercise, how would you attempt to combine the ideas of model performance with increasing training set size and increasing model complexity? Could you create this visualization with something other than a polynomial model? We'll leave that as an added thought exercise. All right. Model validation in practice. We will now turn our attention to practical implementation. In practice, there are a wide number of variables called hyperparameters to consider when choosing a model. Scikit-learn has a useful method called grid search that will iterate through every possible combination of a range of hyperparameter settings you provide as input. Before we get started with grid search, we'll need to switch over from our NumPy polynomial fit method to one in sklearn. Here, the caveat is our actual model will solve for the coefficients in front of the polynomials. We will engineer the polynomial features ourselves. This is an example of feature engineering, which we will visit in depth in a later session. That should be our first topic or so next week, feature engineering. For now, we will just take it at face value. All right, so I'm creating a model. This model pipeline consists of first creating the polynomial degrees of my data set and then fitting them with the linear regression model in sklearn. I'm going to declare a grid search CV object. I feed it the parameter grid of things I want to search through. Okay, so I want to search through the number of polynomial features, and that's going to be done for 10 different values, 0 through 9. So I'm going to choose 0 through 9 different polynomial models. And then for the remaining hyperparameters, fit intercept, I will iterate between true and false, normalize through true and false. So we will we'll sometimes normalize our incoming data, and we'll sometimes fit an intercept to our incoming data. The nomenclature here, for the parameter that I am looking to iterate through, I precede it with two underscores rather, and then the string in front of those underscores refers to the section in the pipeline, right? So polynomial features is the first part of the pipeline, and then linear regression is the second part. All right, so we see this is just syntax here that we use. And then I'm going to feed this into our grid search CV. You'll notice this is pretty similar to what we saw with the CV method up above. I feed it the model. In this case, it's a pipeline, polynomial regression. And then I feed it the parameter grid I want to search through, as well as the number of crossfolds. So I'm going to run this. And now that this is run, I'm going to, again, create a random sampling of my original population data, set that for Y-train and the remainder for X-train. And now I'm going to fit this to my grid object that I declared above. So I'm fitting all of my X data as well as all my Y training data. And then I can look at the best parameters from that search. Looks like the best parameters for what I searched through were to fit the intercept. Yes, fit the intercept. Normalize the data, don't normalize the data. And then do this with a third degree polynomial. To grab the best model from the CV search outcome, we use grid.bestestimator. So I'm setting my model object grid.bestestimator, and then I just use it like a regular model object that we would have used in the past. All right, and here we see the results from that search and training and testing on our remaining data.